In section 2.4, we're going to change direction a little, and we're going to talk about a certain type of numbers we call complex numbers. And complex numbers are useful for people in a lot of different sciences. One use for these is representations of different sort of electrical ideas, like alternating current. But so before we can even start talking about complex numbers, we really need to investigate an idea of what an imaginary number is. So it's a different type of number completely. So if I were to ask you to give me square root of 4, you might say that is 2. In other words, 2 times 2, what two numbers multiplied together equals 4. That's what this radical sign essentially means. But likewise, you could also say minus 2 is an answer, because minus 2 times minus 2, these are the same numbers. Same numbers, same two numbers multiplied together equals 4. So there's two answers to this problem, as we have noticed in the past. Well, that works good for, this works fine for situations where x is greater than or equal to 0, or less than infinity. Can't really be equal to infinity. It's not really possible. But that's not all the numbers on our number line. What about negative numbers? So, what happens if I take the square root of minus 1? What does this equal? Well, the same idea holds. We'll have two numbers multiplied together, and they should equal 1. So what do you stick in here? Well, your first guess might be minus 1. But if you stick in minus 1 times minus 1, they actually equal positive 1 that I wrote here, but I was supposed to write negative 1. But they do not equal negative 1. Minus 1 times minus 1, negative times negative equals positive. This equals positive 1. And likewise, of course, trivially, 1 times 1 also does not equal minus 1. That equals also positive 1. So you can't think of any real numbers that satisfies this relationship. So we had to come up with a new number, and we call this number I. The square root of minus 1 equals this number I. Now, a fellow named Euler coined the term I, but I is an imaginary number. It's not really imaginary. It's more of a number in a different dimension than our real numbers. But it actually exists. It is an actual number. It's not, per se, by definition, a real number, but it is, in fact, does exist. I don't want to use the term real outside of how we're using it with mathematics, so let's just keep it that way. So this means then that I times I equals minus 1. So just like we had our rational numbers sometimes, where we had something we called the square root of 2 that we couldn't represent as a number, and we also had 3.14 equals pi. Sometimes we represent that as a symbol. There's other numbers we represent as symbols, like the exponential. I is now a new number. So we might say this is I squared. This enables us to solve more complex radicals Like, for example, the square root of minus 36. Again, there are no two real numbers that you can multiply together to get the square root of minus 36. But we know from our properties and operations that we can do this. Obviously, we can say this is minus 1 times 36 equals the square root of minus 1 times the square root of 36. So this equals the square root of minus 1 times 6. Actually, if we're only considering the principal root, this is positive. It's actually plus or minus 6. But let's just look at the principal root only. Have a gentleman's agreement that that's the way we're going to look at this unless we decide otherwise, which sometimes we do. So this is really 6. We said the square root of minus 1 was I, 6i. And we can write a whole number line of these things. For example, we could start at 0. We have 1i, 2i, 3i. Let's call this the z number line. That's not a good representation. I'll just say imaginary. We could have decimals and fractions. We could have 2.5i, for example. We could have negative numbers, minus 1i, minus 2i, minus 2.5i, or fractions. We could do fractions too. So we could have any situation where there's a coefficient here in front that is a real coefficient multiplied by this term I. It's a real number coefficient multiplied by the term I. And we can create a whole number line like this, just like we created the x-axis number line or the y-axis number line. It's just a new axis now. Now, a complex number is a real number, say 5, added to an imaginary number, 6i. 5 plus 6i. You can never combine a real number with an imaginary number. They're separate, just like 6x plus 5. You could not combine those two together. But 6i plus 5 is a separate portions of a complex number. So this is your imaginary portion, and this is your real portion. It could be a fraction, it could be a decimal, any real number. It can be square root of 2 even, or some other real number. So often we'll represent this as a, say, plus bi, where a and b are real constants, real numbers. So the square root of minus 24 equals square root of 2 times 2 times 3 times 2 times minus 1, which is equal to, let's divide this up into an appropriate square root of 4 times square root of 6 times square root of minus 1. And so this equals 2 square root of 6i. So if we're going to write this in complex number form, it would be 0 plus 2 square root of 6i. So since we have this complex number line, we can set up an orthogonal axis system like we did for our real numbers. But now, here, remember a complex number is a plus bi, so there's a real portion and an imaginary portion. So what we'll do is we'll create a real number line, starts at 0, 1, 2, 3, so on and so forth, minus 1, minus 2, out to minus infinity. So this is like the x-axis again, exactly the same. but we'll just call it R because it's the real number line. And over here, we'll have our imaginary number line. So in the vertical direction, we'll have positive numbers up, negative numbers down. And we'll call this, it's not a Cartesian, but it's a complex plane representation. And so I can graph complex numbers on this. So I can graph the number, the complex number minus 2 plus 3i, for example. This means I had 2. So 1, 2, I had 2 in the real number line direction. And then I had 3, positive 3, in the imaginary. So 1, 2, 3, up to here. So here's our point. And it's the point minus 2 plus 3i. Well, the point that represents minus 2 plus 3i. And that's typically how you write it when you're dealing with the complex plane. You don't write necessarily it as 2 points, because you might get it confused with rectangular coordinate, with a Cartesian axis. Here I've added 2 more points. One representing the complex number 3 minus I, the other 1 plus 2i. Okay, so since complex numbers are numbers, we need to come up with operations on them, how to deal with them when we're going to do things. Like, for example, what's going to happen when we add and subtract. My hand is moving this on this. When we add and subtract complex numbers. So the general rule is A plus BI is one number. If we add C plus DI, another number, the way you deal with this is you add the reals and then you add the imaginaries and then multiply the imaginaries by I. So add the real coefficients, then add the imaginary coefficients. Subtraction works in a similar fashion. A plus BI. Now remember, A and B themselves could be negative numbers here, but we're considering this whole complex number. So you have to take that into account, and you might have to distribute this negative through your distribute it into this parentheses here. So now you have A minus C plus B minus DI. And it's that simple.